We want to compute the classic Gaussian integral, the area under the curve of e to the negative x squared over the entire real line. First, we give the integral a name, I, so we can manipulate it more easily. Now we square I by multiplying it by an identical copy, but we use a different variable y in the second integral to keep them separate. We combine the two one-dimensional integrals into a single two-dimensional integral over the entire xy plane. Multiplying the exponentials adds the exponents, giving e to the negative quantity x squared plus y squared. To handle x squared plus y squared, we switch to polar coordinates where x is r cosine theta. In polar coordinates, y is r sine theta. A key simplification happens. X squared plus y squared becomes just r squared. The area element changes as well. In polar coordinates, dx dy becomes r dr d theta. The entire plane becomes theta from 0 to 2 pi and r from 0 to infinity, so the integral takes this new form. Because the integrand separates nicely, we can treat the r integral and theta integral step by step. To compute the r integral, we use the substitution u equals r squared. Differentiating gives du equals 2r dr, which matches the r dr we see in the integral. So r is 1/2 du. After substitution, the r integral becomes 1/2 times the integral of e to the negative u. The antiderivative of e to the negative u is negative e to the negative u, evaluated from 0 to infinity. At infinity, e to the negative u goes to 0, and at 0 it equals 1, so the value is 1. That means the entire r integral evaluates to 1/2. Now we substitute that result back into the polar form. The integral of 1 with respect to theta is theta, evaluated from 0 to 2 pi. Plugging in the bounds gives 2 pi minus 0. So I squared equals pi. Because the original integral is positive, I is the positive square root of pi. So the Gaussian integral over the entire real line equals the square root of pi.